First, we will be creating a half adder circuit. For the half adder circuit, we will need two inputs and two outputs. So for the two inputs, we have placed two toggle switches, and for the output, the first output will be sum and the second output will be carry. For the sum, we have used AND gate, and for the carry, we have used XOR gate. Now we will be giving the inputs. Connect the inputs using the toggle switch to the gates properly. And now for the outputs, we will be placing light bulbs. We will be connecting the output to the light bulbs. And for 0, 0, the sum and carry will be 0. And for 0, 1, the carry will be 1 and the sum will be 0. And then for 1, 0, the carry will be 1, sum will be 0. For 1, 1, the carry will be 0 and the sum will be 1. Next, we are going to construct a full adder circuit. For full adder circuit, we will be needing 3 inputs. And we will be needing 2 XOR gates, 2 AND gates and 1 OR gate. Now we will be connecting A and B to the XOR gate. And for the second XOR gate, we will be connecting the output of the first XOR gate. And then we will be connecting the third input to the second XOR gate. And the output, it will be the sum of the full adder. And for half adder, this output will be connected as input. And we will be connecting the third input. And for this AND gate, we will be connecting the first and the second inputs. And now for carry, connect these two AND gates. And for the output, we will be connecting it to a light bulb. For 0, 0, 0, both the sum and carry, both of them will be 0. For 0, 0, 1, the sum is 1 and carry is 0. For 0, 1, 0, the sum is 1, carry is 0 again. And for 0, 1, 1, the sum is 0, carry is 1. And for 1, 0, 0. For 1, 0, 0, the sum is 1 and carry is 0. 1, 0, 1, the sum is 0 and carry is 1. And for 1, 1, 0, we will have the sum as 0 and carry as 1. And for 1, 1, 1, both the sum and carry will be 1. Next, we will be constructing a half subtractor. For the half subtractor, we will be having 2 inputs and 2 outputs. We will be needing 1 XOR gate and 1 NOT gate and an AND gate. Connect the first and the second input to the XOR gate, and we will be getting the difference. Connect the first input to the NOT gate and the output of the NOT gate will be given as the first input to the AND gate, and then connect the second input as the second input of the AND gate, and we will be having the borrow. So now we have connected both the difference and the borrow as well, and for 0 0 we will have borrow and difference as 0. For 0 1 the borrow will be 1 and the difference will be 1. For 1 0 the borrow will be 0 and the difference will be 1. And for 1 1 both the borrow and the difference will be 0. This is the logic diagram for the full subtractor. We will be having 3 inputs and 2 outputs. We will be needing 2 XOR gates, 2 NOT gates and 2 AND gates, and we will be needing 1 OR gate. Connect the circuit as shown here, and the output will be difference and borrow. This is the borrow, and this light bulb, it represents the difference. For 0 0 0 both the borrow and difference will be 0. For 0 0 1 the borrow will be 1 and the difference will be 1 as well. And for 0 1 0 the borrow will be 1 and difference will be 1 as well. And for 0 1 1 the borrow will be 1 and the difference will be 0. For 1 0 0 the borrow will be 0 and difference will be 1. For 1 0 1 both the borrow and difference will be 0. For 1 1 0 both borrow and difference will be 0 as well. For 1 1 1 both the difference and borrow will be 1. Now we will be seeing how to design and implement code converter 1. In the code converter 1, first we will be converting binary to gray code. So if the switch is on, then it represents 1, and if the switch is off, it represents a 0 in binary, and the outputs will be gray code. And for the outputs I have applied light bulbs, and now we will see the connections. First, connect the first input as the first output, and then use this as the input over here and input this over here, and you will be getting the output. In the same manner, input this as well and you will be getting this. So this is B3, B2, B1 and B0, and this will be G3, G2, G1 and G0. First we will be converting, for an example, I will be converting the number 0011 from binary to gray code. So for 0011, the gray code is 0010, and thus we have converted binary to gray code. Now in the code converter 1, previously we converted binary to gray code, and now we will be converting gray code to binary. It is the same circuit, no difference, but now we will be converting gray code to binary. For example, I have taken the number 0010 in gray code, then the number in binary will be 0011. So when the switch is on, it represents 1, and the switch is off, it represents 0, and the light bulbs over here, they represent the binary number. When the bulb does not glow, it represents 0, and if the bulb glows, it represents 1. So for 0010 in gray code, it represents 0011 in binary. Now we will be converting and designing the code converter 2. In code converter 2, we will be converting BCD, that is binary coded decimal, to XS3. So the switches, they represent the binary coded decimal, and the bulbs, they represent the XS3. So in BCD, when it is 0000, in XS3 it is 0011. So we have used 3 NOT gates and 1, 2, 3, 4, 5. 5 OR gates, and the rest of them are AND gates, and it is used to convert the binary coded decimal to XS3. And now we will see another input for 1001. So for 1001, the output is 1100. So for 1001 in binary coded decimal, the XS3 output is 1100. As a part 2 of the design and implementation of code converter 2, we will be converting XS3 to binary coded decimal. So the switches, they represent the XS3, and the bulbs, they represent the binary coded decimal. So this is the connection, this is how it looks. And so now we will take another example, 1011. 1011 in XS3, the output will be 1000 in binary coded decimal. Now we will be seeing the design and implementation of parity generator. In parity generator, there will be 3 inputs and 2 outputs. The first input will be A, B, and C, and the outputs are even and odd. So we will be having 2 XOR gates and 1 NOT gate in parity generator. So when the inputs are 000, the odd is 1 and even is 0. So we will try another input, 001, odd is 0, even is 1. For 010, the odd is 0 and even is 1. For 011, the odd is 1 and even is 0. And for 100, odd is 0 and even is 1. And for 101, the odd is 1 and even is 0. For 110, the odd is 1 and even is 0. For 111, the odd is 0 and the even is 1. So this one represents the even, and the one with the NOT gate, it represents the odd. So now we will be seeing the design and implementation of encoder and decoder. This is the circuit diagram for encoder. So as you can see, these switches, they represent the input, and the light bulbs, they represent the output. This is a 4x2 encoder. So this E0, E1, E2 and E3. So for example 0001, the output will be 11, and for 0010, the output will be 10. That's it for encoder. So now for the design and implementation of decoder, this is the logic diagram. So we will be using 2 NOT gates, 4 AND gates and 4 light bulbs for the output, and for the 2 inputs we will be using the 2 toggle switches. This is a 2x4 decoder. So for 00, the output will be 1000. For 01, the output will be 100100, and for 10, the output will be 0010, and for 11, the output will be 000 and 1. That's it for decoder. So now we will be moving on to the design and implementation of multiplexer and demultiplexer. This is the circuit logical diagram for multiplexer. This is a 4x1 multiplexer. So we will be having 4 inputs and 2 selected inputs, and there will be one output which we have represented using a light bulb. So now for 1 and then the rest of them 0, the output will be 1 as well, and then when the selected inputs are 0, 1, and the second data switch, when it is 1, the light bulb glows, and when the selected inputs both are 1, 1, and the fourth data input is 1, the light bulb glows, and when this selected input is turned off, and when the second data input is turned on, the bulb glows. That's it for multiplexer. So this is the logic diagram for demultiplexer. This is a 1x4 demultiplexer. So for one data input, and we will be having 2 selected inputs, we will be having 4 outputs. For 0, 0, 0, all the outputs will be 0. For 0, 0, 1, the last output will be 1, and then let's try another one. When all the switches are turned 1, it will be 0, 0, 0, 0, 1, and for 0, 1, 0, it will be 0, 0, 1, 0. But when this is also turned off, but when this thing is turned off, all of the bulbs, they do not glow, and for 0, 1, 1, it is 0, 0, 1, 0. Up next, for the study of flip-flops, I have used an SR flip-flop. In the SR flip-flop, I have given the clock pulse as 1, as I need only high. So for example, for 0, 1, the present state will be 0 and the next state will be 1, and for 1, 0, the present state will be 1 and the next state will be 0, and for 1, 1, both the present and next state will be 1. You can also implement it using an SR latch, or you can use it using a NAND gate, as I have done here. So that's it. Thank you so much for watching the video.